Let us take few more question and answer in data structure and algorithm. What are stacks? How can stacks be used to check whether an expression is correctly parenthesized or not? For example, this one is well formed, but these are not well formed. What are stacks? Stacks, it's a ADT, abstract data type, also a data structure. You have a system stack, you can make your own stack. So let us answer this first. A stack is a data structure that organizes data element to how organizes a pile of coins or plates, or there are various examples. The new coin is always placed on the top, a plate is always placed on the top, and the old list is on the bottom of the stack. So when you are accessing the coins or the plate, the last coin on the pile is the first coin which is to be removed. You cannot remove a coin without removing the coins which are above it. Or plates, can you just take a plate which is placed at the last, at the bottom? You'll break all these. So when accessing coin, the last coin on the pile is the first coin removed from the stack. So this one. So if we want third coin, you must remove the first two coins, these two, then only you can go to the third from the top of the stack, and likewise. So there is no way to remove a coin from anywhere other than the top. So only top element in the stack can be removed. So it follows last in, first out order. So stack is used whenever we need to store and retrieve data in LIFO form, LIFO. For example, let us talk about the computers. The computer processes instructions using a stack in which next instruction to execute is at the top of the stack always. And to determine whether an expression is well parenthesized like this, as given in the question, or not, in these two conditions, they are not. Should be fulfilled while pushing, certain condition need to be fulfilled while pushing an expression onto a stack. First of all, whenever an opening bracket is pushed inside a stack, there must be an occurrence of a closing bracket before the last symbol is reached. So whenever a closing bracket is encountered, the top of the stack is popped until the opening bracket is popped out and discarded. If no such opening bracket is found, stack is emptied, and this means that the expression is not well parenthesized. Let us see this one. So what we do, let us check this one. This is a stack. We place first one, second one, and third one. As this one come, these two are matching, so we remove these two. Now we are left with only the first one. These three has been taken care of. Now it comes the fourth one, that is the closing bracket. Now these two are popped off, and when this tag is empty, we say this is correct. Okay. Now let us do it for any of these. Let us take this one. So now you have a stack. Let us have a stack. I paste this. Then the second one. Now this is an opening bracket. This is a closing bracket. So we cannot remove them. Can we? Next one is round. So this is the closing. This is opening. This is the closing. So we can just pop off. Now only the previous one was left. Then the second one will come. And there is no other to carry out the operation. But this is the closing one, this is the opening one. So this stack still has values or still has the tokens even after we have covered all the tokens. So now we can very well say that this is not well formed. This is the algorithm to find out whether our input string is well parenthesized or not. So I hope you will have a glimpse of it and try it by yourself. What is a linear array? Explain how two dimensional arrays are represented in a memory. Linear array. What is a linear array? What is an array first? We have seen arrays also. So array is a name. If you want to make a variable, what do you do? Int a, this variable you make. Now you want to make one more variable, say b. Now I have to make 100 variables. Can you make 100 variables, I guess, in a program? Will it be efficient? Will it be advisable? No. I want to make 100. So I'll take int, name an array, say ARR, and then I'll give a size to it. So there are variables, 100 variables each known by the subscript, that is A0 is the first one. And now you can handle, or you can have 100 variables just by one name. This is linear array. And why this is linear? Because all the values are stored in contiguous memory one by one. You can reach to the second one. In the physical memory also, they are stored contiguously one by one. So an array is a way of referencing a series of memory location using the same name, and each memory location is represented by an array element like this. So an array element is similar to one variable, except it is defined by an index. You have an index that is 0 or 1 or say 99 instead of a name. So an index value is a number used to identify an array element, like ARR. I want to have a 76 value, I'll put 75 here. Array values, the subscript, because array start from 0, so always 76 or 76 number, I have to go to 75. Because it starts from 0, that is why. And it goes up to n minus 1, that is 99 it will go. The square bracket tells, these are the square bracket. This tells the computer that the value inside the square bracket is an index. This is the first one, this is the second one. So how to represent the two-dimensional array in the memory? Two-dimensional array, you can assume it to be a table or a matrix, rows and columns. So the values are placed like this. Let me have a grade be a 2D array named grade 3, 4. What 3 and 4 says? 3 rows. Let me wipe this off. 3 rows and 4 columns. This is what this grade says. So, can you think of how this is stored in memory? Is this stored in the memory like this only, in this form, or any other form? The array will be represented in a memory by a block of how many? 3 into 4, so 12 sequential memory locations. So you can store it row by row, or you can store it column by column. So we say it as row measure wise or column measure wise. So the first set of four array elements, these 4, are placed in the memory, followed by the next 4, then the next 4, and so on, 3 times, because this is 3 into 4. Write a complete program in C to create a single linked list, and write functions to do the following operation: insert a new node at the end, delete the first node. So what is a linked list? Linked list is again the set of nodes with the header pointing to the first node, and the first node have a data item, and the next or the second part of the node is pointing or having the address of the second node, and the last one will be grounded or null, means the second part. Of course, the first one will have the data. The second part will have no address, so it will be null, null. This is how we create a single link, single list structure node. This is a single structure node, that is a single node. We have a data element, this one. We have a link, this one, and we also have structure node P and Q. This is single linked list. We can append a value by doing this, and we can delete the first node. So let me tell you how it is done. So if you understand the concept, you'll be able to understand this code. So if I want to add a new node, I can add it at the first position or at any other position. If I want to add first position, first I have to create a node. So first I create a node, I make a node, and then what I do, I assign this header, which is pointing to the first node, to this node, and now the link of the created node will be assigned to the first node. How to delete the first node? I hope that you'll be able to add in between also, because you just have to point the node pointer to the newly created node and the address of the newly created node to the second node or the next node of this node. How to delete the first node? This is the first node, so very easy. The header is always pointing to the first node. Just point this header to the next node. This is how it is done. So you have to free it. You have to make a temp, assign pointer of Q to temp, and temp link, that is this link, to be assigned to the Q which you have created. This is how it is done. Define sparse matrix. What is sparse matrix? This is not matrix. This is matrix. Okay. So a matrix in which number of zeros entries are higher than the number of non-zero entries is called a sparse matrix. Let us take this example. How many zeros are there? 1, 2, 3, 4, 5. In 9 entries, we have 5 zeros. And how many other values are there? Means non-zero values. 4 non-zero values. 0 prime. Okay. This is a sparse matrix. So the natural method of representing matrix in a memory as 2D may be suitable for sparse matrix, or may save space by storing only non-zero entries. For example, in this, how can we store it? This is our matrix. Now I want to store into sparse matrix. So we have 3, 3, 3. What this first row represent is the dimension 3 by 3 matrix, 3 rows, 3 columns. And what this 4 says? This 4 says the number of non-zero values. How many non-zero values are here? 4 non-zero values. The second row onwards is giving the position and the value of non-zero values. 0, 1, 1, 0, 2, 2, 2, 3. Okay, so we can have 2, 5, 6 9s. These are the values which shows the position. 0, 1, that is first row, second column, so 2 is here. First row and second row and first column. First row, this is 1, 0, that is we have 5 here. Second row, this is second row, 2, 2. Second row, second column, second row, third column, so second row, second column, 6. Second row, third column, 9. So these are the positions of non-zero numbers. Okay. Now give the following in order and pre-order traversal, reconstruct a binary tree. You have these in order, pre-order. These are the sequences, and we have drawn a binary tree out of it. Please try it. This is how you should get. Define hashing. How do collision happen during hashing? Explain the different techniques resolving resolution of collision. So hashing provides a direct access of records from file, no matter where the record is in the file. So hashing is for direct access of records. This is possible with the help of hashing function. There can be various hashing functions like modular division and squaring the midpoint. So which map the key with the corresponding key address or location. So it provides a key to address information. So usually this key space is much larger than the address space. Therefore, many keys are mapped to the same address. Suppose there are 2 keys K1 and K2 mapped to the same address. So when the record with the key K1 is entered, it is inserted in the hash address. But when other record with say key K2 has to be entered, it is a dilemma. We have to insert a record with key K1 because key K1 is already there. This situation is called hash collision. And the broad classes of collision resolution technique are open addressing and chaining. What open addressing says, this is the simplest way to resolve collision, is to start the hash address and do a sequential search through the table for an empty location. This idea is to place the record in the next available position in the array, and the method is also known as linear probing. An empty record is indicated by the special value called null, and the major drawback of linear probe is clustering. But in chaining, instead of hashing function value as location, we use it as an index into the array of pointers. So each pointer acts as a chain that holds the element having same location. Now we see the binary tree. What is the maximum number of nodes possible in a binary tree of depth d? Explain the following with respect to binary trees. Binary tree. So binary tree is a tree in which no node can have more than 2 children. So any node can have either 1, either 2, or none, because this has none. 0, 1, or 2. Maximum of 2 children. Any node can have maximum of 2 children. That it can have maximum of 2 children means it can have 0, 1, or 2. These 3 are possibilities. So this is a binary tree. This is a figure showing the binary tree, which consists of a root and 2 subtrees. Why we are calling them as subtrees? Because this is again a tree with the same condition applied on it. This is TL, that is left. This is T right. Both of which could be possibly empty also. And the maximum number of nodes in a binary tree of depth d will be 2d plus 1 minus 1. And this can easily be found out because, see, if this is the depth, you know that this is 1, this is 2, this is 4. So it goes up to like this, 1, 2, or 2 to the power 0, 2 to the power 1, 2 to the power 4. So just add this. This is a GP, 2 to the power n. And if you add this GP, you'll get the same result, 2 to the power d plus 1 minus 1. So let us see the strictly binary tree and complete binary tree and almost complete binary tree. Strict or strictly binary tree, if every non-leaf node in binary tree has non-empty leaf and right subtrees, then the tree is called strictly binary trees. This means that if this is, say, consider if this is an empty non-leaf node, which is a binary tree, has a non-empty left and right, so it has to have a left and right because it is not a leaf. This is a strictly binary tree because all the nodes which are not, this is a node which is not a leaf node, these two are not leaf nodes, so they have non-empty, so they have left and right subtrees. This is called a strictly binary tree. Complete binary tree, a complete binary tree of depth D is that strictly binary tree, all of whose leaves are at same level, like this. All of the leaves are at same level D. Almost complete binary tree means a binary tree of depth D again, almost complete. If any node at level less than D minus 1 has two children, and for any node in the tree with, say, a right descendant at level D must have a left child, and every descendant of D is either a leaf at level D or has two children. This is your almost complete binary tree. This is very important with respect to the, if you want to save it, this is an almost complete binary tree. Next is what is spanning tree of a graph. So if this is a graph, we can make a tree out of it. You know what tree is? What is minimum spanning tree, MST? Let us execute the Prim's Kruskal algorithm to find the MST of the following graph. So spanning tree is any tree of which comes out of this graph with some edges of graph, which is called as a spanning tree. So if the graph has n vertices, the spanning tree has exactly n minus 1 edges. How many edges? N minus 1 edges. Now the important part is the spanning tree should have all the edges, but because it is a spanning tree, we will not allow the cycles. So minimum spanning tree is a type of spanning tree only, because this is an undirected graph. You cannot make, this can only be done for undirected graph. So it is a tree formed from graph edges. These are the edges. These are edges that connects all the vertices of G. This is a graph G, so it connects all the vertices of G. The minimum spanning tree exists only and only if G is connected. If G is connected, then only you can have a MST. So the cost, the tree which is formed, that is the spanning tree which is formed, having the lowest total cost of the edges or the weight these edges contain, and this is known as the MS tree. MS tree, that is minimum spanning tree. So Kruskal algorithm, let us see, you'll understand more by it, what exactly makes MST is. So let's start. We'll start with a D. And let us see first any node, any arbitrary node you can take. DF. What is the weight? 2. So the first is DF, this one, and the cost is 2. So we write 2. We add it to the tree, our spanning tree. DF. This is the first spanning tree, means the first subtree of a spanning tree. This is our tree. Let us take the second one. F to G. F to G, that means you want to go from F to G, because F we have just taken, D to F. Now F needs to be taken care of, F to G. The cost is 2. We add it to the tree, and we add it to T also. D, F, G. Next, let us take DG, because we have to fulfill all the combinations or these lines, you can say, or edges of D and F. So DG, but what happens here? This DG, it causes a cycle. We'll not take it. If it causes the cycle, we'll leave it. So we'll leave this DG. Then, because now we have come to G also, let us take the G along with what? Any of these? B, so let us say B, G with B. What is the cost? It is 4. The minimum cost is 4. G has, we have taken already, we cannot take this This is 8. We already taken this. So the minimum is 4. So we take this 4. We combine it. Now we have BG also. Next is BD. That is, since we have added B to the tree, we have to see that we connect B with the D. That is this one. Since B already this has been taken, this is cost. Let us take this 5th one. So we add BD to the tree because it will not have any cycle. Then EF, E and F. Can it be added? If I add E with F, this will create a cycle. We will not take it. We discard F, EF. Then we can also have EG. If I combine EG, that will make a cycle. No, we can't take it. So we discard it from the cycle. Let us take AG. AG. 9, no problem. No cycle. Let us take AG. Then next is BC. BC. And what is this? This is 10. We add it to BC. So see, we have covered all the nodes A, D, F, G, A, B, C. All the nodes are covered. And this is our spanning tree. Okay. So what I am saying here is, we are using Kruskal algorithm to find the spanning tree. And this is a simple example how we are going to apply Prim Kruskal for finding the spanning tree. What are B trees? Draw a B tree of order 3 for the following sequence of keys. What are B trees? So B tree is balanced multi-way search tree. It is a balanced, B stands for balanced, and you have a multi-way search tree. There will not be only one key, you have multiple keys here, but they follow certain rules. So B tree of order M is either empty tree or it is an M-way search tree with the following property. Thus, this root has at least 2 subtrees and at most M subtrees. Okay. All internal nodes of T like this, all these are internal nodes other than the root, that means 5 and 10 we are talking about, have between M by 2 or M subtrees. So you can have M by 2 or M subtrees because this is the order. So you take 3 by 2 and 3, that is 1 and 3. So you can only find 1 or 3, that is these internal nodes have between 1 and 3. So they are having 2, no problem. And all external nodes T are the same level. So these are external nodes, or the leaves you can say, they are at same level. So B tree of this order. Next question is complete or construct a complete binary tree with depth 3, which is maintained in a memory using linked representation. Make the adjacency list for this tree also. So how can we make a complete binary tree of depth 3? This is our complete binary tree. We start with a node, we make 2 nodes, then on left and right, left and right, left and right, left and right. This is depth 3, and see this is at 0 level, 1, 2, 3. Okay, so we have, this is the depth of this tree and this is complete. How we can say it complete? Because all these nodes have exactly 2 nodes. All the internal nodes other than the leaf node have exactly 2 nodes, that is left and right. So how we can make the adjacency list of this tree? These are the pointers. Info is 1, this is the pointer. And it has left 2, right 3. 1, 2, 3. So 1, the left is 2, right is 3. Information is A. Then this D has left as 8, but D itself is 4. This is 1, 2, 3, 4, 5, 6, 7. We name it like this: 8, 9, 10, 11, 12, 13, 14, 15. So what about our D? D, let us take B. We have taken. D has left 8, right? D has left 8, right as 7. And let us change the numbering then. So next question is construct a complete binary tree with depth 3, which is maintained in a memory using linked representation, and make the adjacency list for this tree. This is our complete binary tree. You know that complete binary tree, all the internal nodes should have at least, or should have exactly 2 nodes, 1 left, 1 right. These are child nodes. How this is depth is 3. This is 0 level, 1 level, 2, 3, third level. So this is depth. You can say the number of edges 1, 2, and 3 from the leaf node to the root node. This is the depth. How we can make the adjacency list? We number them like this: 1, 2, 3, 4, 5, 6, and 7, 8, 9, 10, 11, 12, 13, 14, 15. So pointer is 1, content is A, left is 2, right is 3. Left is 2, right 3. Let us take any other. 8th. We come to 8. Content is A, H. Left is 0, right is 0. So left is 0, right is 0. All others, all leaf like this. Let us take one more. Say C. C. This is 3. So 3. Left is 6, right is 7. Left is 6, right is 7. This is how we make a adjacency list of the tree. Thank you so much. These were a few more questions on data structure and algorithm. We'll be taking more. Thank you so much.